Hi, everyone. How are you? Hey, I hope you had an awesome weekend. That weather was absolutely incredible. So I hope you got to get outside, enjoy those blue skies, and I cannot wait to see you at the end of this week. So, in order to get ready for when I see you, this week we're going to be learning about a specific type of kinetic energy called electrical energy, which is super fun. So, for today, what we're going to do is you're going to listen to a lesson that I'm going to teach for you right now in this pre-recorded video about electrical energy, a specific type of kinetic energy, matter in motion. What you're also going to be doing is, and let me take you to, I bet you know where, to our Canvas page. If you look at your independent learning for the week here on our agenda, right? You have 2 lessons, Monday, Tuesday, Wednesday. So the part we're working at now is lesson 1. And there are going to be guided notes that are going to go with this lesson that I'm about to teach you. So you can just click on those guided notes. You can download them. And I'm going to be talking about all these vocabulary terms in this lesson. So your guided notes are for you to draw a picture of that term and then tell me, how does that picture relate to the term? So here's the deal. You have 2 choices. If you want to split screen it and do your notes while I am teaching, that's awesome. Or if you want to wait and watch the whole lesson and then do your guided notes at the end, you can do that too. Either way, you're going to want to download these, put them in Notability, and you'll notice what I have here in bright red is submit your guided notes on Canvas. These are due Wednesday evening. Lesson 2 is going to be a second video I made for you, and I've got a virtual lab that you also are going to submit and have that due Wednesday evening on Canvas. So you have 2 lessons this week when I don't see you, which you got to have knocked out because Thursday and Friday when you're at Jones, we're doing labs, and we're going to be doing some circuit building, and we're going to have a blast. And I want you to have a good understanding of these first kind of basic principles of electrical energy. Okay? Okay, so if you want to pause the video and download the note guide, you can. If you want to keep watching now, that's great. Okay, let's get back to our lesson. All right, electrical energy. Okay, so first off in our lesson number 1, we want to figure out what the heck is electrical energy. How do we describe it? How does it move? Obviously, it's matter in motion because it's a type of kinetic energy, but we're going to get into some unique details about this type of kinetic energy. And then remember, the second part of this lesson is your guided notes. You can do those while I'm talking, or like do a split screen, or you may complete them at the end. Either way, you got to submit those on Canvas. All right, so here's your learning goal. Learning goal is I can explain how electrical kinetic energy travels in circuits. Okay, so we know that energy can't be created or destroyed, right? The law of conservation of energy, it just changes form. So when I flip a switch and electricity comes through the wires to charge my iPhone, where does that energy come from? Well, it comes from 2 main sources. Sometimes it comes from renewable energy sources, and those are sources that we've got an unlimited supply of. So I can take these original forms of energy, like energy from the sun, biomass, that's things that were once living, wind energy, geothermal energy, right? Heat from inside Earth's crust, hydropower, and those energy forms can be transformed into electrical energy. So what's great about these is very little pollution, and we have an unlimited supply. Unfortunately, most of our electrical energy we get from non-renewable energy sources. Here in Ohio, most of it we actually get from burning coal. So these original sources of potential energy that we burn, and then heat, thermal energy is released, right? And then water in pipes is heated. Remember that steam goes through turbines, then turns a generator. Then electrical energy is generated. So I just want you to know, right? Electricity doesn't randomly show up. We get it from other sources because energy can't be created or destroyed. It just changes forms. So as we're learning about electrical energy, today I want you to be able to describe electricity using the terms voltage, current, and resistance. I want you to know the difference between an open and a closed circuit, in a series and a parallel circuit, because that's what we're going to be building the end of this week. Here behind you, this is a picture of a circuit board, and there are all these pathways that electricity can flow. Okay, so what causes electricity to move? Well, it's the same idea of when we have two magnets. So I put these two magnets together, and you know magnets have a north end and a south end. What happens when I put the two south poles together? Hopefully you said out loud they're going to push away, right? We call this repulsion, or they're going to repel each other. And the same idea that we use when I'm playing with magnets, knowing that there are forces that are attracted to each other and forces that repel each other, that's what causes electricity to move through pathways. Now, when electricity actually moves, we call this current electricity. I bet you've heard of static electricity too. Static electricity is when we build up these electrons, but they just stay in one place. Current electricity is the flow, the movement, right? It's kinetic energy, so there's motion. The flow of electrons, negative charges, around a closed circuit. So look at my picture here. Here's a picture of an atom. And I hope that you remember that atoms have a negative charged particle on the outside of them that swirls around called electrons. And when I build up these electrons and then these electrons flow, we create current electricity. Now these electrons flow because the negative charges repel from the buildup of other negative charges on one side of a battery. So if you've looked at a battery, you'll notice they have a negative end and then a positive charged end. Well, what'll happen is these negative charges here in this battery, especially when we have a fully charged battery, they build up and they want to push away from each other. Well, when I connect some sort of a wire or a pathway and I have the opposite charge on the other side, these negative charges are able to essentially push out, and now they have a pathway where they are pulled towards the positive charge of the battery. Okay, so when we have this motion, we call this current electricity. Here is, if you are doing the guided notes while I'm talking, you'll notice what you're going to do is for each term that I discuss, you're going to read the definition that I gave you, then you're going to insert or draw a picture that relates to that term. So if our first term is current electricity, the flow of electrons around a closed circuit, you know what I'm going to do? I'm going to draw a battery. Ooh, it's going to be I'm sure not nearly as amazing as yours. And I'm going to draw a pathway for that electricity to flow towards an opposite charge. I might even draw some arrows. Like I said, you might color code yours. You're going to make yours amazing. And then I'm going to describe how does this relate to this picture. Okay, so I'm going to write electricity moves along the wires. So current, which relates back to current electricity, the flow of electrons around a closed circuit. Okay, so that's kind of what your guided notes are. All right, so I've used the term circuit a couple times, but I haven't really explained it. So a circuit is basically a pathway. And we have two main types of pathways. We have pathways that are closed, and then we also have pathways that are open. So let's look at what we've got going on here. This is a simple drawing of a circuit. These type of drawings we call schematics. And it's where I draw a circuit or a pathway for electricity, but I draw it kind of simply. And I draw it with certain symbols like this over here. This is how I draw batteries. This is actually a picture of two batteries because I do a long line and a short line for a battery. This over here is how I draw a bulb. This over here is how I draw a switch. So let's look at this, okay? For a complete circuit to happen, the current electricity has to flow through all the components. So let's see. If this is my negative end of the battery, and then how would those electrons flow? I'm going to basically just trace the potential pathway. And stop. It's kind of like a dead end, road washed out, right? This here is an open circuit. That electricity does not have a complete pathway. And so it's stopped here because this switch is open. It's like the bridge is washed out right here. So because there's a break in the pathway, this is an open circuit and that bulb's not going to light. Just like in math class, you might have talked about open shapes, right? Shapes that are not completely closed versus closed shapes, and shapes that are, right, fully connected and closed. Circuits are the same way. We've got open and closed circuits. All right, so let's look at some of these. Open or closed, will the bulb light? Okay, electrons potentially could flow, and we have a break in the pathway. So this, my friends, is definitely a, nope, I almost circled the wrong one. This is an open circuit. Sometimes we call that an incomplete circuit too. So those bulbs aren't going to light. This one, open or closed circuit. So I'm going to look here, negative charged particles. Those electrons are going to flow into the bulb, out of the bulb. Notice this is a positive end of the battery here. So it would be pulling those negative charges. And then notice here, look, negative end being pulled towards the positive end. So this is a closed circuit. And this bulb definitely will light, because that electricity has a complete pathway to flow. Let's look at this next one, open or closed circuits. Let's think about what would happen. All right, first off, guys, look at this. I've got negative charges coming. That's not what I want. I've got negative charges coming through the wires. Now, remember, opposite charges are attracted to each other. But remember that our initial picture of the two magnets, negative charges are going to repel. Look here where that wire is connected. It leaves the negative end, and it's also connected back here with the negative end. So this bulb, these bulbs will not light because the electricity is not being pulled through the wire, okay? It needs to be attached over here for those to light to the positive end. So that is what we call, again, an open circuit. So here's the first thing we learned about closed versus open circuit. A closed circuit, sports fans, is one that allows current to flow, okay? It's a complete pathway. An open circuit, though, is one where there is a break in those pathways, and that leaves those electrons stranded. So this is an open circuit. I can use switches to open or close circuits. That's what you do like in the walls of your house. All right, so let's describe these currents, or let's describe these circuits now. So first term we're going to use is the term current. Current is a measure of how many charges flow through wires at any given point in a circuit. And I measure this in something called, my units are amperage, which we often abbreviate as amps. So if each of these little, and this drawing is just to help us kind of visualize it, if each of these little particles here represented an electron, which the flow of these is just electricity, and if I were to go through and count 1, 2, 3, 4, 5, okay, counting how many charged particles are in the wire at one time is something we call current. And we know certain wires are able to hold more current than another. You could remember current as being this way too, right? So I have two waterways here. This waterway has a low or slow current. And you'll notice here, this waterway, this cannot hold a ton of water flowing through it, right? It's a nice trickling stream. So this is a slow, or this waterway has a low current. This one here, boy, this waterway can handle a lot of water flowing through it. So this is a much higher current. And if I were thinking about these as wires and I'm measuring how much water is moving through it, right? I would measure that in amps. So a measure of just how many charged particles are flowing through, we call that current. Another term I use when I'm talking about current electricity is voltage. Voltage is a measure of the potential energy of the charges moving through the wire. I measure voltage in something called volts. And we're going to be building circuits Thursday and Friday. And in our circuits, the voltage, or that original potential energy, is going to be provided by a battery. So I bet you know batteries have different ratings on them. Like if I need to, my kids' Xbox controllers are no longer working. They might need more batteries. And so I might need to use AAA batteries. And you know if it needs 3 batteries and you only put 2 in, it's not going to work because it doesn't have enough voltage. AAA batteries are small, so they have a lower voltage. Versus we've got this high-powered flashlight at my house. And it uses these big batteries, and they're called D-cell batteries. And they're batteries that have a much higher voltage. So they have the potential to cause much more change than the AAA batteries. There's a battery in my car. Car batteries are big, and they have a much higher voltage, okay? And so voltage is just a measure of what's the potential energy or the possibility that that original energy, the chemicals in there, can cause change. If I'm looking at a battery, just look over here what's in yellow. In a battery, work is done via a chemical reaction. And in a chemical reaction, what happens is negative charges move across the battery, and then as soon as they're connected to a wire, they repel or they're pushed out, and then they flow around a circuit. Okay, guys, you could think about voltage as being like how big someone's muscle is, right? So if someone has like giant muscles, right, they've been working out, they have a much higher voltage. They have a potential to cause a lot more change than someone like me who definitely does not have muscles like this. Okay, so voltage could be maybe the size of your muscles. So we're thinking about what is your ability to cause future change. And in the case of the circuits we're going to be building, the voltage is going to be the batteries, what size of batteries we're using. All right, also when we're looking at circuits, we look at something called resistance. Resistance is a measure of how difficult it is for electricity to flow through a material. I measure resistance in something called ohms, and there's a really awesome symbol. That's the symbol for ohms. This picture here, these are a bunch of wires, and these little colorful things are called resistors. I add resistors to electrical circuits when I want to slow down the current, when I don't want there to be too many electrical particles in that wire. So, and these different colors mean these different resistors have different strengths, and they can slow down the electricity flowing through those wires. I do that so the wires don't get too hot, right? So they don't have too much thermal energy. Resistors can be added to a circuit to slow the current flow. And also things like a light bulb are also a resistor. So the more bulbs I have on a circuit, the more I'm going to slow down the electrical flow. Motors are a resistor. The wires themselves are even a resistor too. So I remember it this way. I don't know if there are any of you, I hope there are some Star Wars fans. I love Star Wars. Old, new, medium, in between. I'm a huge fan. But here's a picture of the resistance. Right? The whole point of the resistance in Star Wars is this crew was there to slow the work of the Empire, right? So resistors in an electrical circuit are there to slow the work and to slow that current of that electrical energy. Yeah, that's a good looking crew. Okay, so I mentioned the word schematics earlier, and these are just symbols that we use when we're drawing pictures of circuits. Which pictures, when I'm drawing circuits, we call them schematics. And I like these because this makes drawing circuits much easier. Anytime I draw a wire in a circuit, I just draw it with these straight lines. A switch, I draw like this. Here's a picture of a switch that is open. So the bridge is out. It is that current electricity can't flow through. Here's a picture of a switch that is closed. And I use these 2 dots to show that there's a switch there versus just a plain wire. Batteries I draw like this. So I have a longer line and then a shorter line. Some people also draw the positive, right, and the negative charges on here, but when I draw it, the positive end is the longer line, negative end is the shorter line. I draw a lamp or a bulb like this. And if I just put like one of those little colorful ceramic resistors, if one of those is on my wire, I draw it like this. And that's a component just to show that I'm slowing the speed of that current in those electrical wires. All right. So last thing we got to learn about now is types of circuits. And we're going to be looking at, in types of circuits, we're going to be looking at how many pathways are there. So we have two main types of circuits. The first one is a series circuit. A series circuit is a circuit with one loop for the electrical current to flow. So series begins with S, and I always remember it this way. Single begins with S too. A series circuit is a circuit where there is just a single pathway, just one pathway. So if you look at my picture here.
Just a moment. Oh. Okay, I found this.
Siri thinks I'm talking to her. All right, so we look here. In this circuit, there's only one pathway for that electricity to flow. So what happens, guys, is if this bulb burns out, are these other ones going to light? No. So maybe you've had this happen with like holiday lights where when one bulb burns out, then the whole rest of the strand doesn't light. Well, if that's the case, it's because the type of lights you had were series circuits. Now, a pro or a positive thing about having series circuits, they're cheaper, they're easier to create. Later on this week when we build them, it's real easy to build series circuits. You just make one pathway. A con or a negative is if one component doesn't work, let's say this bulb or that resistor doesn't work, the whole circuit doesn't work then. There's no other pathways, no detours. So that's what a series circuit is. It's just a circuit with there's a single pathway for the electricity. A parallel circuit is a circuit with multiple pathways for that electrical current to split apart, then come back together. So look here. In this parallel circuit, the electricity can flow that way. There's one pathway. The electricity can flow that way. There's another pathway. The electricity can flow this way. There's another pathway. So if we have, let's say this bulb burns out, well, we've got these other pathways. So these other bulbs will still stay lit. So a positive or a pro with a parallel circuit is when one component doesn't work, the rest can still work. A con or a negative is building circuits like this are more expensive and more materials are required. Quick question. What type of wiring do you think is used in your house? Do you think there is series or parallel? I hope you said parallel because I know that if like one light goes out in my bathroom, like the other lights in my house I can still use. Now, oftentimes different parts of your house are in different circuits. And so maybe you might have heard of something called like a circuit breaker, where maybe if you've got like your blow dryer and your flat iron and a curling iron plugged in at the same time, and then you turn the bathroom light on, all of a sudden nothing works. Well, what happens is there was too much current flowing through the circuit and that whole circuit was shut down. That way it doesn't overheat. But houses in general are created and they're wired using parallel circuits, multiple pathways for electrical energy to get to the different components of your house. All right, let's look at this picture. Series or parallel? Very good. I hope you said parallel. There are multiple pathways, so the electricity can move that way to get to the bulb. The electricity can move this way. This is definitely a parallel circuit. There are multiple pathways. Let's look at this one. Series or parallel? Nice. Definitely series. Okay? There is only one single pathway for that electricity to flow. You got it. If this bulb burns out, that one's not lighting. Okay. So, what did we learn about? We learned about the difference between series and parallel circuits. Series circuits are ones where there's only a single pathway for the electrical energy or the electrical current to flow versus parallel circuits where there are multiple pathways for the electrical energy to flow. Down here is also pictures, just so you can visualize it, of the schematics. So if I were to build something like this and then ask you to draw it, here's what you would draw it, right? We've got our switch, bulb, battery. All right, last term I'm going to throw at you is the term power. When we look at power, this is the rate work is done. So in the case of a circuit, this means how bright a bulb is lighting. I talk about the power of the bulb. The rate at work is being done. If there's a motor, I might talk about the speed of the motor too, the power of the motor, the rate the work is being done. Now, the power, so how much energy is being transformed into radiant energy or light, or how fast a motor is moving. Power is affected by the voltage, so how much original potential energy it has, and the current, how much electrical energy is moving through the wires. So this is going to be kind of where we're going next week, but I did want to introduce you to these terms. Power, the rate at which work is being done. All right, friends, so here's what I need you to do. That's the end of our lesson for today. You need to complete your guided notes where you draw your picture and why you drew it, and then you're going to submit that on Canvas. Make sure you have that submitted before the end of the day, Wednesday. You also this week, remember, have a second lesson, and you're going to learn about conductors and insulators, and then there's a virtual lab you're going to do, and that is also linked in the agenda. Have all that work done before I see you on Thursday. Let me know if I can help you. Otherwise, I cannot wait to see you. Have an awesome week, guys. I'll talk